Welcome back to the C programming language in action. In this module, we're going to learn about memory management. Thus far, we've only considered the memory pre-allocated by the runtime to service the stack. The stack is a functional and required part of any C and C++ program, as they are stack-based languages. We also briefly looked at statically allocated variables, which receive reserved memory when the program first launches, and that memory hangs around until the program comes to an end. While you can define variables on the stack size tends to be fixed and often quite small, depending on the platform you're targeting. If you need more control of your memory allocations, you need to turn to the heap. But the heap itself is something that must exist at runtime. It can be implemented by a library that reserves some static memory. This is very common in embedded systems, or it can be implemented entirely by the operating system. That is usually the case with desktop operating systems, and certainly the case with Visual C++ on Windows. Let's take a look. Regardless of where it comes from, the heap, or the free store as it's sometimes called, is accessed via a set of library functions. That's right, we've come to the part of the course where we're switching gears and focusing on the C standard library. Although tiny in comparison to the C++ standard library, the C standard library still represents an important set of libraries, functions, algorithms, and constants. We've already been using one of these libraries, the standard I/O library, just for the ability to call the printf function to print out results to the console. That's what the standard I/O header file is, that we've been tagging along all this time. But to use the memory management library, we need to include the standard lib or library header. Now I can call the malloc function to allocate a block of memory from the heap, wherever the heap happens to be. We didn't talk about void pointers in the previous module that covered pointers and arrays. Void is a C and C++ keyword used to denote the absence of type information. This makes sense if you think about it. Malloc, this function, is just a simple memory allocator. It doesn't know what type you might want to allocate memory for. Those 4 bytes I've requested might be for an integer, an array of bytes, who knows? But inevitably, we're going to want to make a decision on what we want it to be, and so we can use a C-style cast again, like we did when we printed out the result of the size of keyword in previous modules. Now I can see. We want some storage for an integer that's backed by the heap. In other words, it's free from the stack. And that's an important point. What if you need to fill in some variable or data structure, but you know or suspect that the usefulness of that variable may outlast the scope in which you've defined it? In that case, you more than likely need to allocate a variable on the heap, as we're doing here. But this allocation function, malloc, could conceivably fail. Your system's allocator may be low on memory and cannot immediately satisfy the particular request. In that case, it will return 0 or a null pointer. Further, this allocation function provides no way to initialize the new variable, as we could for variables declared on the stack, at least not the value being pointed to. The pointer is certainly being initialized, but we can and probably should immediately give it some useful value. Of course, it might be a little wasteful to use the heap to allocate integers, since you can pass them around by value quite efficiently, but you can just as easily use malloc, and perhaps more realistically, to allocate arrays or buffers. Perhaps we're expecting an Ethernet frame, either to send or receive, for an embedded device. Another option might be an array of characters for a WebSocket message. Eventually, we need to tell the memory allocator, the standard library, that we are ready to free the memory, that it can safely release or recycle the memory that we had previously reserved. And that's the role of the free function. The free function only needs a pointer to the starting address of each block of memory. This free function will handle being called with a null pointer. So if you simply pass the result of malloc to free, and malloc happens to fail by returning a null pointer, then free will happily handle that. What free does not handle, and which is a serious bug, is if you mishandle the pointers, these memory allocations, somehow. There are various ways that you can mishandle them. You can, for example, free a pointer twice. You see, even though the message pointer has been freed here, the pointer variable still holds the same value as before. It's just an integer address after all. And the free function doesn't know that it just freed that block and will dutifully try to free it again, but it's no longer a valid block of memory. It could be unassigned, it could be already used by some other thread in the application. It's undefined and it's going to cause trouble. This is obvious in this example, but as the code gets more complex, it may not always be that obvious. Another problem is when you use a pointer that has already been freed. Here I'm dereferencing, again using a pointer after it's been freed. Again, bad things are sure to happen at the worst possible moment. That memory is no longer valid. A good way to remedy such problems is to assign a zero value, a null pointer, to any pointers if the variable names outlive the free function. Now, if we do happen to accidentally use a freed pointer, we'll be greeted with an immediate crash, rather than a possibly silent failure that's hard to detect, much less diagnose. The story of memory management is depressingly short in the C programming language. The C standard library does provide allocation, reallocation, and on some platforms, aligned allocations, but that's about it. On Windows, malloc and free simply pass the requests along to the operating system, which has a very intelligent and efficient fixed block allocator up to a certain threshold to improve small allocation performance and virtually eliminate fragmentation. And C++ itself also simply calls malloc and free from its abstractions, but C++ offers some invaluable abstractions which really are game-changing, and we'll cover those a little later in this course when we consider the road from C to C++.